Me and my baby alien toy are back to talk about tension again. Now, as we already know, tension is a contact force that points in the direction of a string or rope. And it turns out that we need a couple of assumptions to deal with tension forces. The first one is that we want our string or rope to be massless. Now, the reason for this assumption is that if you have, for example, an object which is accelerating, like so, each point of the string will end up having a different tension in it because it will need to act a bigger and bigger force depending on how far away from the object it is in order to accelerate the extra mass in the string. Another thing that we will need to assume is that the string is inextensible, which means that when you stretch the string out, it doesn't change in length or size. Now, real strings and ropes do in fact flex just a little bit when you pull on them, but this is sort of an idealization that we want to make, because if the string ends up extending, then each object that it's connected to might not move quite as far as you are expecting. The other thing that is a useful approximation to make is that the tension is uniform throughout the rope. Uniform. And what this says is that the tension in any given part of the rope is going to be equal. So over here and over here and over here, all the tensions are going to be equal to each other. Now, this is probably the most tenuous of these assumptions, but only in a particular case. If, for example, you drape a rope or a string across a pulley or something like that, if there is, for example, friction between the point of contact where the string is touching the object, or if there's any rotation that happens in the pulley, you can get that the tension in different sides of a rope as it goes over a pulley are different. So for right now, we'll be making the assumption that the tension is uniform, and later in the course when we get to rotational motion, we'll see how to account for including rotational motion of a pulley into our model.